kind of the idea of tonight is do a brief introduction to binary exploitation. I've thrown some stuff up here so I don't make a horrific mistake as I'm going and confuse everyone. Out of curiosity, who has done anything with like buffer overflows or binary exploits? Okay, the cabinet. Perfect.
How about what classes have people taken? Like, what do you talk about? Like, I don't even know what class we talk about this in.
I don't think this would be in any class.
Shit.
I think we mentioned it like once in like 185.
I was gonna say 185 would be the closest I could think of.
Yeah, I think we like mentioned it once.
So this is probably the ooh scary, don't use get because that's a scary function. They tell freshmen and then never go in the weeds why.
Yeah, sounds about right.
So perfect, this will be new information. This is the stuff that I really love to do. So I'd love to talk about it if people have questions after. Should I put this on?
Up to you.
I can put this on.
It picks it up fine on the table, so that I noticed.
Okay, so kind of the plan for this meeting is I will do like a 20-minute introduction to how computers work on like the really low level for programs, and then David will do a kind of a walkthrough of a CTF challenge he did that utilizes some of this information. Any questions, comments, concerns before I get started? Small group, so you know.
It's pretty intuitive.
A much more personal overview.
Yeah, much more personal overview. Okay, so I'm just gonna have to assume that everyone here has done programming before, because I can't go that far back. So we have a pretty simple function kind of program. Main has two variables, passes it to foo. Foo does some stuff. It has a character array. It calls get. It does stuff. It returns. Pretty simple. I'm sure everyone can follow that relatively easily. Has anyone ever looked at like what it actually, the memory, so this would be like in RAM, that a program looks like? Has anyone ever?
I mean, they covered 227.
Okay, so some stuff in 227. I honestly wouldn't be surprised if a lot of people just kind of toss that out of their head because it doesn't actually really help you in programming. And a lot of people are very efficient at forgetting things that aren't actually useful to them in normal life. So here's kind of the layout in memory of what a program looks like. For computers, everything is binary and everything is in the same file, same area. So you'll have the .text section, which is all of this compiled down into machine codes, ones and zeros. And then you'll have data, which we don't actually have in here, but think of values that don't change. If you print out hello world is going to be stored in here. You have the stack, which is going to hold all of the information for each function. And then you have the heap that's going to store stuff like global variables. If you've ever had to call malloc in C, it's going to allocate stuff on the heap, so that's where you're going to store stuff if you use malloc and free and stuff like that in C. So we're going to take a quick look, mainly focused on the stack because that's the easiest part to kind of get a hold of. Heap stuff gets really hard, and you can't change data or text. So we're less interested in those in the beginning. So going from here, we're going to have stuff beneath here in the heap or in the stack. For calling a function, we have two variables. To pass those over to the function, everyone's familiar with the stack data structure. You put stuff on, you push, pop. So you're going to push A, then you're going to push B, and then this right here is some place in memory. In text, there's some value of where that code is running, what instruction the processor is pulling out of the text section. So you're going to also push that. So when the computer finishes your function, it knows where to go. Then you're going to start foo. You got an array of 5 chars, and then that's going to create that area. 1, 2, 3, 4, 5, and they go the other way. 1, 2, 3. And I'm not starting at 0, but we'll be fine. I suppose I have to erase it anyway. 0, 1, 2, 3, 4. And then it calls gets on the array. Does anyone know, people know what gets does? You take input, fgets I think is the one they teach you to use for C. Think input for Python. Does anyone have any idea of why gets is dangerous? Yes?
Because it doesn't take an amount of data you want to take in, it just takes everything.
Yeah. So, is everyone familiar with how strings in C end? They have a null byte. They just have all zeros. So get assumes you're a very nice person, and it will just keep taking whatever you give it until there's a null byte. However, this char has 5 spaces in it. So let's say, we'll be nice, we'll give it hi. And then this will be a null byte at the end. So we'll store h, I, exclamation point, null byte. It does stuff with these values. It returns. The computer looks at this return value and goes, oh, I go here, and then it just starts doing more stuff. Now, what we're going to do is, what if we aren't nice? Let's say that we give it, the favorite is just a bunch of A's. So A, da, 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 da. So we're going to write A, and get will just let you write whatever you want until you give it a null byte. So it's going to overwrite this value to be an A and just continue on. Computer will probably still work for a little while. But then, after you're done with stuff, you're going to return to a location. Where are you going to return? You're going to return to location A. Or because return pointers require, I think it's 8 bytes, you're going to return to point A. And then, so the computer will go try to figure out where A is. A is not going to exist as executable code, and it's going to crash. Is everyone following so far? Let's say we have a function evil stuff. This, I don't know, prints passwords. Or it opens up a shell, so now you get terminal access. Or it does something that the programmer doesn't want you to do without going through some other checks, or doesn't want you to do at all. In CTF, this is normally going to be like a print flag function. So this is going to be more of a disassembler type of thing. You can find what is the value here. Is this X beef? So then for get, you can simply write a bunch of A's, dead beef, and then want, your function returns. It's not going to return to here, where the programmer thinks it should go, because you've overwritten the return address. The computer does whatever you tell it to do. And the computer is told, start executing code at this location. You overwrote that location, so you control where that computer goes to execute code. This is kind of like the basic stuff, but it gets super fun in here, both mitigations and stuff like that. David, are you ready to go?
Sure, yeah.
So I can give it over to David, who had an example from, was it this last week's or a week before?
2 weeks ago was this is from the Allies CTF. How do I turn it on? But yeah, so that's kind of the theoretical, like abstract spiel of stacks and overflows and all of that. Super useful to understand it, but I always like to try it out myself, get a better understanding through doing it, and the safest way to do that in real life is through a CTF, which is why I started that Discord and why we have all those people doing it. Yeah, projector will take a second. But, so yeah, we had a CTF 2 weeks ago, 2 weekends ago, that involved a challenge that just gave you, well, they actually were really nice and they gave you the source code for the program as well as the compiled version of it. But when this gets up, I can show, I did a write-up for the CTF on my website. So if there's anything that I don't explain very well that you would like to review, that website will be up and you can go and check that out.
You can also ask questions to
Asking
us
questions
now
is
or
great
in
too.
Slack.
Yeah, because that'll probably be better explaining because I'm more or less going to walk through the walkthrough and do some live demos of using tools. I guess the main tool for today will be GDB, the GNU debugger. I don't know if anybody's ever used that, but it is like comes standard with most Linux installs, and it's super useful for stepping through programs and doing like a dynamic analysis where you're going through and you're peeking at memory and you're changing the little memory addresses to see how the program messes up and what you can do to it. So, okay, projector on, HDMI not being selected. Two HDMI cables neat. Ooh. Yep. Sweet. I will mirror. Oh, sorry. Okay. That should be good. Okay, so this is the website where I try to keep all of my write-ups for CTFs we've done. I only have like 5 or so right now, but whenever we do ones and I find interesting challenges, I throw them up there. So it's www.davidjwolf.com. It's just a GitHub Pages thing with whatever. So the basic challenge description is up there, and all they said is, I'm using Arch, by the way, BT dubs. So not a super descriptive problem, but the files that we were given are C Canary and so we were given Canary as a executable file, or C Canary as an executable file, and then ccanary.c, which is the source code for the execution file. And then I added a test flag file that would just be for testing locally, so we know if our exploits are working. And I'll actually delete payload because that will come later. So this is more or less the basic setup for this problem. So for going into it, going from the ground up, we need to read that source file. Normally, they don't give you the source code, and you have to go through a bit of reverse engineering using tools like Ghidra, which is a really awesome GUI-based decompiler. But for this one, they just gave us the code, which is awesome. So we can throw that into whatever text editor we want and take a look at what it's doing. So I usually start at main and look through this. So here we have our main function, and we can see it's calling a printf function with quote. It's reading in some data and outputting some data. So there's a bit going on here, and it's usually best to run it a couple times without breaking it so that you know what it does when it's not broken, so that way you can break it. Because a lot of times I'll just jump into exploiting it somehow or throwing in a bunch of garbage data and then it crashes, but I don't actually know like what it normally does. So if we just run the C Canary binary, we can see it just prints out the word quote and takes in some data. Hello world. And then it outputs some data. So it says canary chirp chirp, good burb, and then gives you a little formatted output saying that you said this in 2021. So that is standard for whatever garbage data you'll throw in there. Same sort of thing applies to it. So a good place to start. We can come back over to the source code, and now it makes a little bit more sense. We have our printf for quote, showing us where we're going to be inputting data. It calls a quote gets function, which we'll have to look at a little bit because that's not like a standard. It's not like gets or fgets or something. That's a custom function. We'll have to check that out. And it's calling it on data.yourInput, which is a struct. And then we have a call to data.callCanary, another printout, which is that good verb, and then it prints out the data. And I guess most importantly from this screenshot, we can see that if the data.give_flag, if that resolves to true, we just get the flag. They just give it to us. So that is the end goal. And it's always good to have a goal in sight for these CTFs. So we now know that the overarching goal for this challenge is to make data.give_flag be true. So with that in mind, it's important to look at, well, what is data, I guess? Because in C, and I don't remember if this is covered in 185, do you guys do structs or structures in 185 for C? A little bit. Structures are just a C thing to try to make objects, because the big thing about C is that there's no object-oriented programming. That's what C++ is for. So structs are like a super low-level object where we can just store attributes. So we have your input, which is set to nothing at first, an array set to nothing. Call canary, which is set to a canary value, and give flag, which is set to 0, which in C is false. And that value's never changed. So we know we need to do some sort of trickery or magic with the binary to get that to work. Because if you just run this, you're never going to get give flag to be 1, because it's hard-coded to 0 at the beginning, and then nothing changes it. So this is instantiating one struct. At the very top of the program, we get a bit better of an idea of what this structure is doing, because here we can see the description of it, or the actual definition, sorry. So before was instantiation, and then this is the description. So we have our struct. It's called data. It holds 3 different attributes. The first one is a char array of 32 bytes, so it's 32 characters long, titled your input. After that, we have a void pointer, which just points to a function, essentially, and we call that call canary. So that'll be interesting to look at because it's actually a function value. That means that the program is going to jump to that function at some point. And then we have an integer give flag, which is used, as we saw later in the program, to determine if we should be given the flag or not. So with that sort of basic analysis out of the way, I've kind of, in my mind when we were doing the CTF, I've narrowed it down to 2 possible exploit paths. Either we need to just do a buffer overflow to change that give flag value to be 1, or there could be some trickery with format strings to leak values, and that was a whole can of worms that luckily we didn't have to get into. But I guess from here, the important thing to understand is where the name of the challenge comes from, C Canary, and why there's so many references to canaries, which are generally associated with birds, and why that's in the function. So who knows what a canary is in relation to programming, not necessarily the actual bird. But there is a tie to them, I guess. If you want to do that. Nick.
Does anyone know canaries in coal mines and what their uses go for?
Yeah.
Oh, let's see.
They would put them down in the mines because of the gases that could be down there because you can't smell them.
Yeah.
So the canary would die
Yeah, it would die.
before the humans would die, and the humans would know to get out.
Yes.
So kind of the same idea is used here.
Yeah, so that's where the real world analogy and why we call them canaries in programming. Basically, a stack canary is generally some magical value that only we as the programmers and only the program knows. It's this magical value, and if we never change that value, once we set it on the stack, we never change it, and if anything ever changes it, we'll go back and check, and we'll know that something's broken. I mean, some data overflowed, or there's some corruption in memory because this value should never change. We checked it, it changed, something's wrong. So if we were to go back to the stack analogy here with Nick's awesome drawing, we would have, still have user variables up here, but before we get to the sensitive stuff, like our return address, we would put something on here, something magical, something, like beef, Bobo. Something weird right here, and that way we can build user data up here, and rest assured, because whenever we read in data, we just check this canary value, and if it isn't changed, then the program's okay to keep running. But if it has changed, we have to exit and close the program immediately because something bad's happened. So if you were to do this A example again, you would write all A's in here, and then this would get overwritten, and something would become an A, and some number of A's in here, and then we would know that everything's broken. So hopefully that's pretty clear. And that was a huge hint going into this program. They named it Canary. There's a bunch of references to Canary. There's going to be something here we have to avoid. So I guess that takes us back to the main function. Now that we know what this structure is actually doing, we see that it's reading in our data into that your input field, which was that 32-byte char array from here. It's reading into there, and right after that, it's doing a call to call Canary, which is that function pointer we saw on the struct. So up there we have your input, and then call Canary is the Canary function, and then there's giveFire. So presumably, when this program initializes, Canary is going to be set to some function that actually does something. And in this example, it's set to, up here, there's void Canary. This just prints out Canary chirp chirp. It's a really simple function, kind of just a placeholder, but that's what it's set to when it first runs. So with that in mind, let's run the program with something weird. So we know that our array for holding data is only 32 bytes long, and there's no checks on the bounds. So if we run it and we do, you can use Python to generate repeating strings of characters pretty easily, which is nice. So if we take A and times it by 33, which is one character longer than the array that was assigned to us, we should see a segfault or something weird happen. I guess we don't know for sure that it's going to crash, but we do know that it will be something that is undesirable behavior.
You can also probably just type it in.
Oh, Lord, yeah. Or I just freeze my terminal.
Are you going where you've got the screen frozen for us?
Oh, no, it's frozen for me, too. I can't move my terminal anymore. I might have tried to paste something that wasn't supposed to be pasted. All right, we'll just fire another terminal.
The dangers of live demos.
Yeah, but whatever, we're back at it.
Super small.
So, yeah, we'll just run Canary, and we'll take Python. I think I had, yeah, so we'll take this, and we'll just pipe that into Canary instead of trying to do copy into the board. So, yeah, running Canary and passing in that user input. So when we pipe it in there, it's just doing the same thing as us typing it, except we don't have to type 33 A's, and I don't have to worry about copying and pasting. But here we can see we actually do get a seg fault, which is promising. So a segmentation fault means that we kind of tried to do something that the program is really angry about. Usually it means that we're trying to jump to a memory address that isn't actually code. So that kind of gets back to this idea of text and data in the stack. So when you're in here and doing all this memory stuff, there is no discernible difference between instructions and data. The compiler just reads them, and if it's at a point in memory where it's supposed to treat something as an instruction, if there's data there, it's still going to try to treat it as an instruction. So this is good news and means that we're probably on the right track for exploiting this, because now we can crash it and we can control some sort of, we can control the execution of the program somehow. Now the tricky part is we need to actually control that, we need to control the function. We need to control where that function is going in a meaningful way. Right now we've just overwritten that data with some random stuff. We need to know how we're overwriting it and where it's going. So here's where we introduce GDB as a tool. So GDB is the GNU debug tool. Probably there's no man page for it, but
It uses some funky other thing.
whatever. It's got its own set of things. It's a very long and complicated man page, but a lot of you don't need. All you need to know is that if you do GDB and then pass an executable file, like our Canary, you'll hop in here, and now we can run this program with a debugger attached to the process, so we can monitor its memory, we can tell it to stop executing, we can step the instructions one by one, and we can view the raw assembly. So the first thing to do here, we can do info functions and see the functions that we have access to. This program was really nice, and when they compiled it, they didn't strip the binary. Stripping it makes it a smaller program and is more efficient, but we get rid of all these nice symbols, like main. So if we wanted to go into main and see what was happening, we can set a breakpoint at main just with break main, and then run the program. and see we've started the program, and then we reached our breakpoint at that big memory address in main. So we can do disassemble command, and it will give us a huge output of all of the assembly instructions that are being ran inside of main. And it's really hard to read this, and nobody would ever expect you to be able to read this the same way you read like C code or something. There's a reason we have higher level programming languages, because this is impossible to read. But we can get a good idea of what's happening and where we're at in the program by using some of the decompiler or disassembled notes. So we see a lot of calls. Whenever we see this call instruction, we're calling a function. And then usually, if it's a known solid function, we'll get a symbol for it. So this is the puts in the, what's PLT stand for? Shoot, the PLT is like some known,
Layout table.
yeah, it's some like standard library that's used across a bunch of C programs, and puts is a very common program or function name, so that's put into these little comments. So at first we don't know what's happening here, but if we look back at our source code, we can see we're looking for like a printf and then a call to quotes gets, and then there should be a puts and the call canary false somewhere around there. So these are the four lines of code that we're really concerned about when looking at the disassembly. So in here we can see, oh, right there, we have a call to printf, which corresponds with our quote string probably. Then we have right after that a couple steps of magic and quote gets, some other garbage, puts. So that looks like we're right in this area. 2 puts, a printf, and quote gets. So that means that between quote gets and call canary, or in puts, we have our call canary function. So going into this, we will look at, well, let's just run it once without modifying the data, and then we can take a look at what data is supposed to be there. Because it'd be a good idea to know what's in the canary normally, and then how we're changing it. So if we put a breakpoint right before, or right after this quote gets function, we can copy this memory address. Again, hopefully that's copied correctly. And we can break at that memory address right there. The star at the beginning is used the same way it is in C to denote that this is a memory address and not a like raw value. We break there, we get our second breakpoint, and we can continue the program with the C. And now we're back into normal execution. So we have quote as a parameter. We can do hello world, hit enter, and we're at our second breakpoint. So now, right here where this arrow is where we're at. Right after the quote gets function is returned. And now we're just doing some assembly where we're moving the AL register. And more importantly, between this quote gets and this puts PLT, so the quote gets is where we read into our input, puts PLT is where it prints out the next thing. There's another call command, and that's being called at some kind of weird address that isn't as standard as the other ones. And it's 18 bytes off of the base pointer for this stack frame. And so the base pointer is usually at the top of a stack frame, and then that refers to something else. So there's a good chance that that address contains our canary value, because it's being called between those two functions, and it's stored in a place we would expect for a struct. And again, a struct is stored sequentially. I mentioned this at the beginning, but I don't know if anyone was here. If you had an int and then a char array of some value, and then you had another int at the end of it, similar to how we have it set up right now, where we have a char array, a pointer, and an int, it will lay those out in memory sequentially. So if this was the stack, this int would go up here, the char array would take up the next some bytes, and then the int at the end would also be here. So the way we have it set up is we have a char here, and then before we get to our int, we have a pointer to a function, which is our canary. And then we have our int that checks if we're getting the flag. Because again, just to reiterate where we're at, we're trying to overwrite that last value in the struct to be a 1 to get our flag eventually. It's really easy to lose track of what the goal is when you get into the weeds of the assembly, but that's the overall goal. So now that we're here, let's take a look at this memory address, because that might be something that we want to see what the default one is. So if we do x/x, or we'll do x/3x, $, I'll explain this command in a second. I just gotta make sure I type it right. $R RBP minus a hex 18. Okay, so this command is saying the first X is for examine, and then a /3x says look at the first 3 blocks and treat them as hex. So the first 3 4-byte chunks, or whatever those are, of hex, read those, and then read them from the memory address RBP minus 18, which is where this function is getting called. And here we can see if we use the concept of endianness, which I don't know, has anybody talked about endianness in any of the classes for data? So that's just how the data is laid out, whether you read data from high to low or low to high. In this instance, we're using the type of endianness that requires you to read backwards. So this first, or the second block anyway, if you read left to right, is the highest data byte, or the most significant bits, and that goes next to this one. So we have these 2 chunks of data that are our canary. Those are the magical value that is going right here, and that's preventing us from overflowing anything. Because right now what we saw is we overflowed that canary, and it segfaulted because it just crashed. Probably because it was calling this function, and that function pointed to our data, and it got really confused and threw up its hands and said, I'm done. So now we know we have these bytes as data into our program. We have those as the default secret values. So that makes sense how we're getting what we're looking at here when we do this examine command in memory, and why it's important that we have those. Because now if we have those, we can get enough A's to get right up to the canary, and then we just fill in the canary value because we have it now, and then we can keep overwriting because the function will come back to the canary and say, is everything okay? It's like, yeah, I haven't changed, but everything around it has because we just overwrote it and then overwrote it with itself essentially. So yeah, that's a big step, is getting the canary. So we can do that. And now we can actually just continue the program, and you'll see it exits the same way it did when we ran it outside of the debugger because it's just a normal program and we didn't overflow it. So now an important thing to do would be, let's go ahead and quit GDB. And we need to generate a payload. So we have those memory addresses. They're 00005555, 55555521 is what we need to overwrite at the end of our number of A's. So we'll start, I always use this Python command to generate payloads. And we have our 33 A's here. If we just pipe this into a file called payload, so, or sorry, not pipe, redirect. Piping puts in to standard input and is used, the next program uses it as standard input. Redirect will put it to a file. I'm not sure if everybody's familiar with that, but that's what we're doing. So we put that into a file, and now if we cat our payload file, we can see it's just a bunch of A's. And we can run that with GDB if we do GDB Canary. Let's break at main again, and then run, and we can pass in our payload file. So run, and then the reverse pipe to pipe a file into a program, or reverse redirect into the payload, and then we'll run it. We're at our breakpoint in main now, and we can get the memory address we want to stop at again, which would be right between the quote gets. Here we go. You would probably want to have these stored in a notes pad or something, so you don't have to keep disassembling and copying and pasting, but for this quick demo, it'll be okay. So we'll break there again, continue. Okay, so we can see that the quotes prompt was outputted, and it doesn't show anything because we're getting our input from that payload file we passed in. And if we just run the same command where we just examine that memory address at RBP minus 18, we'll take x/2x $RBP minus hex 18. Double check that, okay. So now we have something different here. That's like totally different than the data we saw in here when we ran it normally without overflowing. And a handy feature in GDB is we can replace this X with whatever format we want to print it in. And if we do S, it'll try to treat this output as a C string. And if we do that, that's pretty interesting. So now we're looking at these 2 bytes of data, and instead of just being some garbage memory address, we can see it's AA, a backslash and a quote, backslash and an N, dash U, 2021, and then the second byte of data is just a blank empty string. So like that's a really good sign because we're clearly overwriting data and going into that. So Now, the only thing left to do is for us to replace this overwritten data. Oh, also, I guess the only reason that there's you see 2 A's at the end of that followed by a bunch of garbage is because our, that quote gets function, this quote gets function here, where they actually include a little comment that says fix me, there's an overwrite issue. Big hint that this is a buffer overflow. Inside of here, it appends this like quote marker and then a new line and U 2021 and all this stuff. So that's why when we put in those A's, we don't just see the A's. There's also other data being put in here. But now that we have this, we can really just go through and start generating a more nuanced payload. Instead of just throwing as many A's as we can at it and breaking it, let's try using what we learned about that canary. So assuming everybody already wrote down what that original canary was, we'll just put that into the payload. I didn't write it down either, but I think I have it in my, oh no, my batch history gets cleared. Yeah, okay. This, I think, will work. So this is a Python program I had, or a one-liner that I had saved from when I was testing this offline. But basically all this is doing, so if you remember that previous payload, or that previous canary value had like a ton of 5s and a bunch of other garbage before and after it. Not a lot of those are printable characters. So to ensure that we can print those characters and pass them in, because you can't just like make a string that has these specific values because they're non-printable characters. If you tried to do that, you'd have a bunch of weird symbols that your computer wouldn't know how to handle. Copy and pasting, that's a nightmare. So I always use Python, and using their sys buffer write function, you can give it raw bytes, and it will print out the raw hex values into a file. So if we take this, we've got our canary here that's kind of written backwards, where it's 55555555. This is a memory address backwards, because you can see all these 5s match up to all the 5s up here for the memory address. And then it ends in 2, 5, and 10, or 52 and 10, which would be the location of our canary function. So if we run this, we get another new content in our payload. We piped that, or we redirected that to the payload file. We read it out. We now see we have some printable characters like R's and a bunch of U's. But what you don't see is that at the end of that, there's a bunch of binary data that can't be represented as a string, and we can't copy and paste it, and it's garbage. So we can try running this now and seeing if this would give us something a little bit better to look at. So we can do GDB ccanary again, and we can, well, let's just try running it with payload, and it's segfaulted. Okay, you're gonna see some live debugging, because I don't think that was the right payload. That one's definitely not right. There's also a chance that this changes between, yeah, okay. Okay, let's go back, and so what I'm trying to do right now is unsuccessfully trying to reuse my previous commands, because like, heaven forbid I don't do this live, but I think it has an issue because the canary probably changed, which is something that we'll get into in a second, but let's just run this, and we'll just have to get the canary out of memory again. Oh, plus 1. Oh. And
You made it pointer.
this is decimal 100, right? This decimal 100. Okay. Nick coming out with the speed strats. Okay, so now we can check that same thing of RVP minus 18, x/2x, $RVP minus x18. Okay, so we can grab this, and we can see it's still pretty much the same as what I had originally. It's a bunch of 5s, and then it ends in 52 and 10. So let me make sure I got that. Okay, so I copied those two out. What was that? Oh, wait. So if we were to rearrange these, we would have something like this, where we have, taking into account the endianness is all this is doing. If we rearrange them here, we would have something like this as the valid memory address we're looking for. So it's 2 0 bytes and then 52 and 10 at the end. which this is the correct function. I think I went 1 2 back in my master's history, but rearranging the memory address we got out of memory, we get that. And then does everybody see how that maps to here where we just kind of flip the bytes around? This is something that I hate and Nick hates, and there's only 2 ways to do the endianness. Either you do it this way or you write the whole thing backwards. So I usually just chest both of them until one of them works. But so this should be the correct payload. Python should write that byte array out to the file, and then we can just pipe it in. So I'm gonna, okay, so let's run that again, cat payload, same stuff in there, and now we'll go gdb canary, run again and pass it in our payload file, and hey, that's different output. That's the output that we like to see. So before we even started messing with that original, like, there's that third struct argument that was the get flag thing. Kind of forgot about that, but this payload still works. So it's, instead of doing the normal thing where it just says U2021, it says here's the flag, and then it prints out our offline testing flag. So like that's awesome. That's exactly what we're looking for. Because, and I guess just to wrap things up, or to wrap this part of it up anyway, the reason we don't have to mess with this give flag variable very much is because in C, it's getting set to 0, which is false, and then anything other than 0 is true. So we overrode it with some data, with probably some A's or some of that -U 2021 stuff, and because that's not 0, that's a true value. So when it gets down to here, it sees that, oh yeah, that's true because it's like an A or whatever, which isn't 0, and we can give our flag, and it calls the system function. So that's awesome. I guess we just need to copy our payload, and then normally in these CTFs, they have a remote server that you connect to and you run your payloads against. So we should just go on there and huck that payload in, right? And then we get the flag, and then we're all happy. And the 3 hours it took to get to this point were all worth it because we can turn that flag in. But
That is an important note. We're going super fast right now because we've already solved this.
yeah.
These things can take hours when you're used to them. So if you try to go onto it and it takes you a while, do not be discouraged. That's normal.
Yeah, so definitely, and anybody who was there at the CTF can attest that we spent just a long time messing with this. And it was fun, we learned some stuff. I had never messed with a stack pointer or a canary on a stack that was also a function pointer. Usually it's just some magic number. But either way, the moral of the story is this worked offline for us, this payload, because we knew what this canary was. We can just look in memory and say, oh, this is the canary, put it in and run it. The problem is that's not consistent. That's not the same, it's not guaranteed to be the same between runs of a program. There's things like ASLR, address space layout randomization, which if that's enabled when you compile a program, there's no guarantee where anything is going to be. It can throw data all over the place, and the memory address will be totally different.
And that was created to stop us from doing this.
Yes.
Like that's a security thing because people like to do this.
Yeah, that was the old cat and mouse game of security and protections, but people started overflowing data, and they're like, well, if we put the same thing in the same spot every time, yeah.
What I'm understanding from this canary is it's like a key that's in the binary or in the stack, and if you change anything in it, if you change that specific canary, it's going to know that someone's tampering with it.
Yeah.
And so you have to keep it exactly what it is and not mess with it.
Yes.
Okay.
Yeah, and that's generally the idea with this, and that's why if this was a more standard canary where it was literally just the word beef on the stack or something, that would be super easy because that means that in the program running on the server, it should be the same thing, and they should be checking the same thing so we can overwrite it. The fact that this is a function pointer puts in a wrench in our plans because that's going to change between systems depending on your kernel and the layout of where you're running it from. I mean, like, the environment variables you have set could change where it is in data. So we can't just throw the payload we just generated to work locally onto the server. And we found that out the hard way, and that's where we died. We didn't solve this challenge during the CTF. But, solving it's fun, and it's a confidence boost. But I guess the important part is you go back and you learn from why we didn't solve it. So this is where I'm going to defer back to my write-up. This talks at the end. This is going through pretty much everything we just did, seeing that we overwrote data, we've got all sorts of stuff, and here's us winning with the local flag. And here's me explaining that this is where we died, and nothing happened afterwards. But after the function, or after the competition rather, had ended, people post their own write-ups of people that are much smarter than me and solve all the challenges. And they showed that, oh, well, it turns out there's like this one function that you can use that's like, it's called vsyscall. In vsyscall, I'm not even going to try to explain this properly because I don't fully understand it. If I understood it, I would have solved this challenge probably. But basically, it's a function that's stored in the kernel of an operating system, which is underneath of everything. It's like the heart of it. And inside of that kernel, there's a vsyscall, which it's a special function because it's not only in the kernel, but it also gets mapped to program memory, which is rare because normally kernel functions don't have an address in a program because they're not in the program, right? They're in the kernel, which is like totally separate. But this special one has a map because it's used so much. So they wanted a faster way for the program to reach out to it. So instead of calling a kernel handler that would call the kernel function eventually, we just call it straight from memory. So if you knew all of that, and you knew that this was compiled with the kernel, they mentioned at the top they're using Arch Linux, which is a distro of Linux. If you knew all of that, you could just guess that the function you're supposed to go is at this address. This all F's, a 6, and then some zeros. This is some magical address that references that vsyscall. So if we replace the canary with that value, we can get it to go to that function. It will just return because it doesn't have any arguments because we didn't put any on it. And then we can overwrite the other data and get our flag. So that's what ended up happening. Here's the final flag for it. This might not work on your system is what the flag says, and that's very apt because I couldn't get it to work on my local system. Like I tried that payload and a bunch of other stuff I read online about it, and I couldn't find any of them that worked for my specific layout because my kernel was slightly different than theirs. I was doing this on Windows at first, and now I'm on Linux bare metal, and I still can't get it to work, so I don't know. You can read my final thoughts on it, but I didn't like this challenge because it came down to guessing one function out of all of them that just happened to be in the same spot. But yeah, so I hope that made some sense. That's the more technical, like hands-on demo of how stacks work, why stack overflows and buffer overflows in general are a thing, why they're bad, what a canary is, and yeah, some of the fun stuff that we get to do in the CTF. So it can also be just a plug for doing more CTFs because they're a lot of fun. And I learned literally everything I talked about through doing them because like we were talking about, I don't think there's a class that necessarily teaches this, at least not one for underclassmen or undergrads. Probably not.
I think, so class 431 that I'm in right now might pretend to teach it, but it's both a bad class and it doesn't go in depth on anything. So,
Yeah.
Maybe they'll make something now that cybersecurity is an actual major rather than just a minor.
Imagine that.
But
Classes for us. So any questions? Any general thoughts, ideas, things you would have done differently, things, are you excited for another CTF? Yeah.
What websites are you doing now?
Yeah, this is my website for a couple write-ups. I'm going to erase some of this stuff just around here, but.
Did you just use Vimtext?
What?
Did you just use Vimtext?
Vimtext. For the hosting the website?
Yeah.
No, this is through GitHub, using GitHub Pages, and it's all written in Markdown. So it's like, I don't know. It's super useful. You can make it look super nice with like minimal effort. So
yeah, GitHub lets you host websites for free. They're relatively simple ones, but if all you want to do is build a portfolio of here's the stuff I've learned, I have one as well. I'd highly recommend it.
yeah.
It works well. It's free.
This is where you can see if I went too fast or if I went too slow and you hate me now. This is where you go.
Did you make that whole thing with markup? Like,
No, just the posts pretty much. There's a bunch of themes you can use. Use like Jekyll, right? That's one of the options for a
Jekyll.
theming engine.
Jekyll is the overarching thing, and then people are nice enough to put out free themes.
Yeah, this is
it's
a free
like
theme.
So there's like a default, like, here's the CSS and the HTML layouts and how the JavaScript works, and then you just feed it markdown files and then just make something that looks pretty.
Yeah, it's super easy, and like I made a website using just HTML and CSS, and it was terrible, and it took forever, and it looked awful. So like I would totally encourage this. If you don't have any need for like login pages or user interaction, just GitHub pages is like the fastest thing to do. And it's in a repo, so if you ever need to edit, you just pull it down and you've got everything there. So yeah.
So are most of the CTF challenges, do they mostly use C?
What?
Do they mostly use like the C programming language? Because like function was all in C, and I'm like.
I wouldn't say most of them. I'd say a lot of the times the reversing and the binary exploitation ones are, just because it's really common.
Okay.
But if there's, a lot of the scripting ones or like encryption or encoding ones will use Python. That's another really common language.
There's a bunch of web challenges, and together you'll find PHP and JavaScript.
Yeah, and more Python for hosting websites. Or you'll find really weird ones like whitespace or like, just obfuscated programming languages that nobody actually uses.
Game Boy.
Game Boy, yeah, we had a challenge. We had a challenge at the last CTF that was a Game Boy file, and you had to like open it up in an emulator that was able to use like cheats, and then you could expand the screen, and there was a flag stored outside of the playable area. It was crazy, but yeah, they really get creative with their with how they orient challenges. But yeah, I think that's pretty much everything we have. We're pretty much at time.